Continue with our discussion of heat transfer. We have seen plane wall, then we have seen cylindrical geometry. Basically, we have seen heat transfer in an annulus. Then we can think of another application where we have got a spherical geometry. So, spherical geometry. Here also we assume that the thermal conductivity remains constant and there is symmetry as far as heat transfer is concerned. So, that is why heat transfer will take place only along the radial direction. Okay. So, one can think of spherical cells, let us say, I mean it is very difficult to have a 3-dimensional diagram. So, basically what I am drawing, that is a spherical cell section taken, and this is the outer cell, inner cell and outer cell. So, this is R1, capital R1, this is R2 and any intermediate radius R. So, we will have q dot is equal to minus K A dt dr in this case also. Actually, here I have written capital R, but smaller, but this is the same thing. This area is the spherical cell area at any intermediate radius r, and we can write it minus k 2 pi, sorry, this is 4 pi r square into dt dr. This is 4 pi r square dt dr, that is the surface area of a spherical cell. And then we will have q dot into dr by r square, that is equal to minus k into 4 pi dt. So, what we will have after integration? Can you tell me? No, here logarithmic term will not come, it will not come here.
Minus 2, then n minus n plus 1 by r. It will be minus 2 by 1 upon r. Yes.
So, basically we will have, I can write down the final expression. So, 4 pi will remain and then it will be T1 minus T2, where T1 is the temperature at the inner radius, T2 is the temperature at the outer radius, and we are assuming T1 is greater than T2. All right. And then what will be the R term? Okay. K we have forgotten, so K we have to put, and then we will have R2 by R1, R2 minus R1. That is what we will have. Then at the top we will have R1, R2. So, this if we put, then what we are getting 1 by, that is what you are probably mentioning, that 1 by 1 by R1 minus 1 by R2, 1 by R1 minus 1 by R2. So, this will come from integration. Okay. Let us not bother too much regarding this, because this we can do in any moment from the basic laws of integration. So, this is how we will get the heat transfer for plane wall, for cylindrical wall and for spherical geometry. Now, one can try different other things, and one can write the generalized expression of conduction equation. Generalized form of conduction equation. So, here let me write this is in Cartesian coordinate, because in cylindrical polar coordinate and spherical polar coordinate we will get different expression. Actually, this equation one can derive easily, but I will not do that. Let us say we have got some sort of a control volume which is like this, a 3-dimensional control volume, and then we can have, well, we can have accordingly our, this is x, this is y, and this is z. So, x, y, z, three coordinates we can have, and then if we apply Fourier's law of conduction and make some sort of energy balance, assuming that there is only conductive heat transfer, then we can write down like this. Q dot minus of minus k d2t dx2 minus k d2t dy2 minus k d2t dz2, that is equal to rho c dt d tau. What I have done, I will tell you. I am not going for the rigorous derivation of this equation. So, I have considered the time rate of change of the temperature within this volume, and I have considered heat transfer along any direction of the Cartesian coordinate. Along with that, I have considered that in this volume at each and every point heat is being generated. Okay. So, this is generation, this is actually volumetric generation. So, sometimes people put either QV or Q triple prime, because in a volume this is the rate of generation of heat. Okay. This is conduction and this is time rate of change of energy, time rate of change. So, for steady state this term will become 0. All right. So, let us try from this one. So, what we have done, if we simplify this equation, we will have Q by K plus d2t dx2 d2t dy2 plus d2t dz2, that is equal to rho c by k dt d tau. I hope you know all these quantities. Rho is the density of the material, or should I write it? Rho density, then C or Cp, whatever it may be, specific heat, K conductivity, T temperature, tau time, and then Q, this is volumetric heat generation. Well, so let us see whether from this generalized equation what we have done earlier, whether we can get it or not. So, steady state we will get dt d tau is equal to 0. Then no heat generation, so Q is equal to 0, and then if we have only in one direction, so d2t dx2 is equal to 0. All right, d2t dx2 will be equal to 0 if it is one dimensional heat transfer. So, then we can integrate it. So, dt dx will be constant. So, dt dx is equal to constant. Okay. So, no heat generation, Q is equal to 0, and obviously here when we have derived this equation, please look into this particular expression. Here this is valid for constant conductivity. Not only constant conductivity, the material is also homogeneous and isotropic. That means conductivity is not changing from point to point, it is not changing for different temperatures, it is not changing with temperature. So, if we have such type of material that it is homogeneous, it is isotropic, and we do not have any heat generation, we are considering steady state. Moreover, heat transfer is one dimensional. So, then in that case we are having d2t dx2 is equal to 0, dt dx is equal to constant. You see, that is what we have got. This is two wall, one is kept at T1 and another is kept at T2. The temperature profile will be something like this. So, dt dx is equal to constant. Okay. And obviously, from here we can get what is the rate of heat flow. So, I mean generalized equation is also valid for these special cases which we have derived. Of course, if you look into this equation, this is not fully generalized. Here one can again make it more generalized, taking different conductivity in different directions. That is also possible. One can take kx. So, in that case it will be not k into dt dx2, but d dx of k dt dx. We are not going into those details because that is not within the scope of this particular course, but one can make it fully generalized, and the derivation of this equation is also not very difficult. One has to only consider Fourier's law of conduction along different directions. All right. Now, another important aspect one can get is like this, that let us say we are considering a steady state case, but there is heat generation. So, steady state with volumetric heating. One situation could be you are analyzing the heat transfer of a, let us say, slab or cylinder where electric heating is there. So, the material itself is a conducting material. Through this we are passing current, and then we have got Joule heating in the conductor. So, it is volumetric heating. So, in that case what will be our equation? My equation will then be Q by K into plus d2T dx2, again one dimensional conduction, let us say, is equal to 0. Okay. So, then you will see we will have a nonlinear temperature profile. We will have a nonlinear temperature profile. Okay. But these are only mathematics. There is no I mean not much of extra physics is involved in it. The physics is same, Fourier's law of heat conduction, but after that one can have different mathematical expression depending on different situation. So, this is what we like to do, or we like to discuss in conduction heat transfer. Now, then we go to convective heat transfer. Now, convective heat transfer, here there will be physical motion of the bulk medium. In the conduction there is no physical motion of the bulk medium, but in case of convection there is physical motion of the bulk medium. So, obviously, it will take place in a fluid. So, what is happening? For energy transport, as there is bulk motion, the hotter fluid is coming from its own place to the colder region of the bulk of the fluid, and colder fluid is moving from the from its own place to the hotter region or to the high temperature region. So, there is some sort of intermixing. Okay. But if we look at the molecular level, there also heat transfer is taking place by conduction. That means, one fluid molecule to another fluid molecule which is just adjacent to it, heat transfer takes place by conduction. But what is the difference with conduction, pure conduction? Is that in conduction all the molecules of the material, they are at its mean position. Here the molecules are having motion. So, in conduction the one molecule can give energy only to its neighboring molecule because its position, mean position is fixed, but in case of convection it can give to its neighboring molecule, energy to its neighboring molecule, but at the same time it can change its place, change its position. So, initially what was at time t, what was its neighboring molecule? At time t plus delta t, its neighboring molecule will also change. So, obviously, in convection we will have a higher rate of heat transfer. What I mean to say is like this: suppose there is a fluid medium, if we consider heat transfer only by conduction, we will have some rate of heat transfer, but if there is convection along with it, so we will have a higher rate of heat transfer. The example is, we know that we produce sometimes hollow bricks because we have air in between that, and this creates, as air is a bad conductor of heat, this will create some insulating effect. So, this is true as far as this gap is small. When the gap will be large, then by convection air can also create some good amount of heat transfer. All right. So, one has to remember that in convection the mode of heat transfer between two adjacent molecules is conduction, but over and above there is a motion of molecules due to the bulk motion of the medium. All right. So, basically if we see the interplay between conduction and convection, it is like this. Let us say this is a surface, and on this surface there is flow of fluid. So, adjacent to the wall we have 0 velocity. due to no slip condition. So, here the heat transfer is purely by conduction. After that, the molecule, fluid molecule which is getting heated up, so that will have some motion. Next molecule, it will transfer the heat by conduction, and then the other molecule which is away from the wall, that will have higher motion, higher velocity. So, it will have the capability of transferring the heat to a larger distance. So, we will have a greater transportation of thermal energy from the wall to the bulk of the fluid. All right. And as in case of fluid flow, I have discussed already that adjacent to the wall we will have a strong gradient of velocity, which is known as boundary layer. Let us say this is a flat plate and we have got fluid flow like this. So, we have got a boundary layer like this. So, this is the boundary layer. So, similarly, this is called velocity boundary layer. All right. So, similarly, adjacent to the wall we will have also a boundary layer where there will be change in temperature, that is called thermal boundary layer. So, let us say the wall is hot and the adjacent fluid is cold. So, we will have a boundary layer like this. So, the temperature will change like this. Highest temperature at the wall, which is T wall, here it is 0, and this will go up to the fluid temperature, which is T infinity. It will go up to the velocity of the fluid, which is U infinity. So, here the velocity will change from 0 to U infinity, here it will change from Tw to T infinity. So, when there is a fluid flowing past a wall whose temperature is different from the fluid temperature, we will have two boundary layers. One is a velocity boundary layer and another is a thermal boundary layer or temperature boundary layer. These two boundary layer may be extended up to different level. They may not coincide with each other. In most of the cases they will not coincide. Either the velocity boundary layer will be thinner or the temperature boundary layer will be thinner. Well, so let us try to understand the convective heat transfer and then we will discuss certain rules for determining convective heat transfer. Now, in this regard, the law which was given by Newton long ago, that is still the guiding law for convective heat transfer, that is known as Newton's law of cooling. Basically, in engineering practice and in number of scientific practice, we are interested when there is a heat transfer between a solid body and a fluid. We are interested in that phenomenon. And in that case, Newton's law of cooling says that Q is equal to H A delta T. So, delta T could be like this. Let us say there could be different thing. Let us say this is one phenomenon where this is a body and this is the fluid which is flowing through it, okay. Or the phenomenon could be something like this, that this is a conduit of any arbitrary shape and fluid is flowing through this. So, this is known as, this is one situation and this is another situation. This is known as external flow and this is known as internal flow. External flow and internal flow. All right. See, in all these cases, Newton's law of cooling is applicable. In any case, it is applicable. So, only thing is that one has to define these quantities properly. So, let me define it. Q dot is the rate of heat transfer, as we have already mentioned. H is the coefficient of convective heat transfer. A is the area. So, here obviously A is the surface area, here A is the not cross sectional area, perimetric area, inner perimetric area. Okay. So, that is also a surface area, because heat transfer in convection in these cases, this is a surface phenomenon. All right. So, surface area, basically it is external surface area, this is internal surface area. Though there are, from fluid mechanics point of view, there are difference between these two phenomena, I am going to explain that. All right. So, H is coefficient of convective heat transfer. Then A is the area. Delta T is the temperature difference. Now, this delta T has to be defined properly, or rather it is like this: H and delta T. A is more or less unambiguous, A is the physically what surface area you will get, but H and delta T, they are to some extent related to each other. The way you will define delta T, you will get a particular value of H. It is like this. Means when there is external flow, over a flat plate. So, what we can have, let us say the flat plate is kept at a constant temperature T wall, and we have got fluid flow. Fluid is initially approaching the plate with a velocity, with a temperature T infinity. So, there will be thermal boundary layer, and ultimately at the edge of the thermal boundary layer we will have T infinity. So, this is T wall and this is T infinity. So, heat transfer is basically between the temperature difference T wall to T infinity. So, obviously our Newton's law of cooling, where Q is equal to HA delta T, in this case delta T will be TW minus T infinity, TW minus T infinity. But let us say we have got a flow inside the pipe wall. So, what is happening here? The temperature profile is something like this. At the wall we have got high temperature, at the center we have got a lower temperature. All right. If we are heating the fluid with the help of the, passing it through the tube, that can happen. Let us say the tube is electrically heated, and through this we are passing the liquid or gas, or let us say it is a boiler tube where it is getting radiant heat and the fluid, which is water, it is being passed through the tube. All right. So, in this case, what could be our delta T? For simplicity's sake, let us take TW is constant. But what is the fluid temperature? Basically, some difference between the surface temperature and the fluid temperature. What could be the fluid temperature? what type of mean temperature? Somebody is telling that mean temperature, but what type of mean temperature we will take? Again I am telling that it is H is dependent how we define the temperature. So, one temperature is surface temperature, but how we define the fluid temperature. So, in this case what is taken, that we take the bulk mean temperature. So, there is a temperature profile like this. Let us assume some sort of imaginary process. Let us say we have got some imaginary starer here. We star this. If we star this, well mix this, then what we will get? A constant temperature. Let us say the constant temperature I show like this. This is the constant temperature we will get. So, this mean temperature we will call as bulk mean temperature or mixed mean temperature, or sometimes it is called mixing cup temperature. So, we take that temperature and then we define H. If we could have taken some other temperature, we could have got some value for some other value for H. All right. Now, let me now proceed with H. So, this equation we could understand that this is Newton's law of cooling. This is a very useful information, because suppose I want to calculate what is the rate of heat transfer, I have to use this information or use this equation, and in this equation most crucial thing which we should know is H. Convective heat transfer gives us the means by which we can determine H. So, convective heat transfer is all about the determination of H. This point should be made clear. All right. In convective heat transfer, we discuss different methods. I am time and again I am emphasizing the same thing. In convective heat transfer, we discuss different methods, different situations, so that we can determine H. All right. Well, so determination of H. Determination of H. Now, how do we determine H? Now, thing is that mainly there are three methods of determination of H. One is experimental. Second one, experimentally one can determine H. Then second one, analytical. And third one is numerical. Actually, these last two methods are interrelated. The last two methods are interrelated. See, basically when we try to determine H, what we do, one is experimental, that you measure. I have written this law, Q dot is equal to H A delta T. So, A is known from the geometry, Q dot the input heat transfer or the rate of heat transfer, you should have some method of determining. Let us say you are going for electrical heating, you know it, or let us say you are heating by condensing steam. So, you know the incoming steam temperature, or the condensing steam is at saturation temperature. So, you know its latent heat and you measure the condensate. So, you know the heat transfer rate. So, Q dot should be known by some method. A generally it is known from the geometry. Delta T temperature measurement you have to make. So, that is how you can determine. This is the experimental technique. Then analytical and numerical. only the method of solution is different, but basically theoretically we are doing. So, what we have to do? We have to, in both the cases, we have to determine the temperature profile first, temperature profile in the fluid. For determining the temperature profile, what we have to do? We have to consider three conservation equations. One is conservation of mass, another is conservation of momentum, and third one is conservation of energy. So, three conservation equations I have to write down. Sometimes if the velocity profile is known or velocity information is known, only conservation of energy I have to write down. So, from there I will get the temperature profile. Now, the temperature profile one can get by analytical method. So, in most of the cases analytical method is not possible. So, we go for numerical technique. So, this is the main procedure, but though the details of the procedure is not suitable for this particular course. So, we do we do the theoretical analysis like this, that all the conservation equations, three conservation equations are solved to determine the temperature profile. The solution technique could be analytical or numerical. All right. Generally, we get analytical solution only in limited case. Let us say we have got laminar flow in simple geometry, we can get analytical solution. But if the geometry is complex, if we are going for turbulent flow, so most of the cases we have to take the help of numerical technique. So, from there we determine H. All right, I will not discuss these techniques, but let me show, let me discuss some other thing which are important in connection with convective heat transfer. So, H, convective heat transfer, it is customary to express this convective heat transfer in a non-dimensional form, and the non-dimensional number which gives the convective heat transfer, coefficient of convective heat transfer, is known as Nusselt number. So, Nusselt number, it is denoted by Nu is equal to H L by K, and we can see that dimensionally it is matching. Okay, let us quickly do that. Q dot is equal to H A delta T. So, what could be the dimension of H? Dimension of H. Let us determine the dimension of H. Joule or kilojoule per
meter square.
Per Kelvin, per degree Kelvin.
Is there any time unit? This is rate of heat transfer, not heat transfer, rate of heat transfer.
That is watt. That is Q dot is kilojoule per second. So that is watt. Kilowatt per meter square per Kelvin.
Okay. Then what is the unit of H?
H is equal to that unit, same unit.
We have told H, sir.
So H is equal to kilowatt per Kelvin per
Per
meter
meter
square.
per Kelvin.
Oh, you have told that.
Yes.
So,
coefficient it will be dimensionless.
no. Coefficient is not dimensionless. Coefficient is not.
If you say coefficient of heat transfer, then it will be so many heat units per unit time per unit area that can be told.
Okay, that is what we are telling, and then we are defining a non-dimensional number which relates this heat transfer coefficient, and that non-dimensional number is your Nusselt number. So, in the unit of H we are getting meter square.
Meter square.
per meter square. Okay, rate of heat transfer per meter square. We can get it like this: H is equal to Q dot by A into delta T. And again, conduction equation if we write, so we can write Q dot is equal to K A dt dx. All right. So K is equal to Q dot by A by delta T into dx. This is what we can write. So if I take a ratio, then you will see that HL by K, that is becoming a non-dimensional number. All right. HL by K, that is becoming a non-dimensional number, and that becomes the Nusselt number. Now, Nusselt number, basically the heat transfer coefficient is expressed in terms of Nusselt number, and there are either analytical expression for Nusselt number or there are correlations for Nusselt number. All right. The correlation which we get for Nusselt number, that will depend on number of parameters. So this Nusselt number, which is nothing but HL by K, where H is the heat transfer coefficient, L is the characteristic length, and K is the conductivity of the fluid. Let me write H convective heat transfer, coefficient, L characteristic length, and then K is conductivity of the fluid. So, K is the conductivity of the fluid, then we will have HL by K, it will be different for different situations. Nusselt number will be different for different situation. All right. Basically, H will depend on a number of parameters. So, let us say what are the parameters on which H is dependent. H will be dependent on the velocity of the fluid V, okay, on the specific heat of the fluid, on the density of the fluid, on the viscosity of the fluid, on the thermal conductivity of the fluid. Temperature difference will not come directly, but indirectly it will come because all these properties, they are temperature dependent. And again, there are some other factor which I cannot just write by symbols, like whether it is internal flow or external flow, what type of geometry it is, what type of surface characteristics are there. So, there are other factors. Okay. So, similarly, we can have Nusselt number as function of, let us say, capital F, of several non-dimensional parameter. As Nusselt number is a non-dimensional parameter, we will have Nusselt number as a function of, or we can express Nusselt number as a function of several non-dimensional parameters. Several non-dimensional parameters. Okay. Now, let us see what are the different situations just to have some idea. So, H or Nusselt number, or let us say convective heat transfer coefficient, that depends on type of convection. So, generally there are two types of convection. One is your type of convection, one is your forced convection, and another is your natural or free convection. So, as the name suggests, in the forced convection we have got flow field which is generated by some external agency, by some fluid mover. So, we can have either a pump or a compressor. So, we have got the fluid motion generated by some moving body, or it is generated externally. Whereas, natural or free convection, it is due to the difference of density, mainly it is due to the difference of density, and some sort of body force field should be present. Gravitational field is one of such body force field by which we can have natural convection. Generally, when we mention natural convection, we refer to the situation where there is a body force field and due to density difference we have got some sort of a convection current, but there is no external moving agency for the fluid and there is no other external agency which is responsible for creating the velocity field. Now, of course, one can have different type of convection. If we have, instead of the gravitational field, suppose we have got electrical field, we can have similar type of phenomenon. But let us not discuss in that, discuss those issues. So, basically forced convection, here the fluid motion is created by some external agency, and in natural convection it is due to the density gradient and density change, that is due to temperature. So, temperature difference itself creates some sort of a motion. So, there are two types of convection, forced convection and natural convection. Again, two types of situation I have discussed, one is internal and another is external. So, in all these cases I will have different type of relationship for Nusselt number. Basically, if it is forced convection, I will have Nusselt number is equal to some sort of a constant C1, then Reynolds number to the power N1 and Prandtl number to the power N2. This type of a relationship I will get. I am not giving these numbers because this number will vary from situation to situation. This constant, then there is one number here, then there is another number here. For forced convection, I will get this type of a relationship. Okay. What is Prandtl number? Reynolds number we are familiar with. What is Prandtl number? Prandtl number is PR is equal to PRANDTL, Prandtl number, and this is equal to mu Cp by K. Mu is the viscosity, Cp is the specific heat, and K is the conductivity. Okay. So, this is what we will get in case of forced convection, and in case of free convection we will get Nusselt number is equal to some constant, again let us say C2, Grashof number, there is one non-dimensional number to the power N3 let us say, and Prandtl number to the power N4, where GR is equal to Grashof number, and it is given by beta g L cube delta t by nu square. Beta is coefficient of thermal expansion, then g is the gravitational acceleration, then L is the characteristic length, delta T is the temperature difference, nu thermal expansion coefficient of thermal expansion, and nu is equal to mu by rho. So, we know actually nu is called kinematic viscosity and this is mu by rho. Now, from situation to situation, these C2, N3, N4 will vary. So, it is no point giving these numbers, okay. But this is how we have got correlations, and using these correlations one can determine Nusselt number. Then knowing the characteristic length and conductivity of the fluid, one can determine age. Then using Newton's law of cooling, one can determine what is the rate of heat transfer. Okay. So, I think with this we can conclude our discussion on convection. Radiation we will not discuss much, but little bit in tomorrow's class we will do.